There are two special types of right triangles that whose angles show up a lot, and the size of the triangles are pretty easy to get, or at least the ratios of the size of the triangle are easy to get. The two special triangles are a 45, 45, 90 triangle. 45, 45, 90. We've got two 45 degree angles and a 90 degree angle. Because we're going to be using these a lot in the future, even though degrees are probably a little bit more comfortable for most students, radians are actually much more common. So I'm going to also write these in radians. This is pi over 4, and pi over 2. Okay? And this is one special right triangle because we have two angles that are equal. Okay, this is an isosceles right triangle. And the two sides that create the right triangle, or the right angle, are they have the same length. And so the most basic size, if you will, of a 45, 45, 90 triangle is one where that length is 1. Now, of course, there are many different sizes. We could increase the size of this triangle and keep a triangle but similar, where, you know, for example, the length of this side might be 2, and then that would also be 2. But this is a good structure to remember, because then we know, of course, that when we're doing the trigonometric functions of angles, we don't care so much about the individual lengths. We care about the quotients or the ratios of those lengths when we divide the two. The other special right triangle is the 30, 60, 90 triangle. Okay, and again, in radians, that's pi over 6, pi over 3, and pi over 2. And for this, you'll notice that the shortest side is half the length of the hypotenuse, and the other leg is the square root of 3 times the length of the shorter side. Okay. Now, if you don't remember these numbers, you can come up with them by creating special types of functions. The 30, 60, 90 triangle actually comes from half of an equilateral triangle, okay, where that's a length of 2, and if this is 1, then all together, okay, that's a length of 2 as well. So this is an equilateral triangle, which has, of course, all angles equal to 60. Half of that is 30. And so then you can, you know, of course, the length of the 1 and the 2, and you can find the third side by using the Pythagorean theorem. Now, that's not necessary. Most people will just memorize these numbers, and that's kind of what I recommend, because they come up so much, and you're going to need to know those kind of on the fly quite a bit. Okay. The 45, 45, 90 triangle is super easy to get because you just create the two sides that you know are equal. So the easiest number to set those to be would be 1. And then you can solve for the length of the hypotenuse by using the Pythagorean theorem. Let's go ahead and use those special right triangles to find 6 trigonometric functions of these given angles. So find all 6 trigonometric functions of 60 degrees. So I'm going to draw a special right triangle, and it doesn't really matter the orientation that I do it. So I'm going to do it like this, which is slightly different than the way it was shown on the previous slide. But I've got a larger angle, which is the 60 degrees, and a smaller angle, which is the 30 degrees. And then we can label the sides. So the shortest side is 1, and the hypotenuse is 2 for a 30, 60, 90 triangle. And this last side, if you don't remember what it is, you can use the Pythagorean theorem to get it, but it is the square root of 3. So now I'm finding the 6 trigonometric functions of 60 degrees. So relative to this angle, here's our opposite side, here's our adjacent side, and here's our hypotenuse. And so now we can find those 6 functions. We've got sine of 60 degrees. Sine is opposite over hypotenuse. And that is square root of 3 over 2. Cosine of an angle is adjacent over hypotenuse, which in this case is 1 over 2. tangent of 60 degrees, that's opposite over adjacent, which is the square root of 3 over 1, or in other words, just the square root of 3. Then we have the cosecant, and I'm going to go ahead and just use the fact that I know the cosecant is the reciprocal of sine. So I just flip that around, it's 2 over root 3. If you'd like to rationalize the denominator here, you are welcome to do that by multiplying by the square root of 3 on top and bottom. And we get 2 root 3 over 3. The secant function is the reciprocal of the cosine, which is 2 over 1, or just 2. And the cotangent function is the reciprocal of the tangent function, which will be 1 over root 3. And you can rationalize this denominator as well if you'd like. Multiply by root 3 over root 3. And we get square root of 3 over. For the 6 trigonometric functions of 45 degrees, we can draw our special right triangle of the 45, 45, and 90 triangle. And so these are our 45 degrees, 45 degrees. And the side lengths that we memorize are both of those equal sides are 1, and the hypotenuse is the square root of 2. So for our 6 trigonometric functions, sine is opposite over hypotenuse. Okay. We're doing this relative to 45 degrees, which is either one of these. We could pick either one to label our sides as opposite, adjacent, and hypotenuse. I'm going to go ahead and use this one down here. So here's our opposite, and here's our adjacent, and our hypotenuse. So opposite over hypotenuse is 1 over root 2. Cosine of 45 degrees, cosine is adjacent over hypotenuse. And that's also 1 over root 2. Tangent of an angle is opposite over adjacent, which is 1 over 1, which is just 1. Then we have cosecant of an angle, and cosecant is hypotenuse over opposite, which is root 2 over 1, which is just the square root of 2. Secant of an angle is hypotenuse over adjacent, which here is root 2 over 1, which is also root 2. And cotangent of an angle is adjacent over opposite, which here is 1 over 1, which simplifies to 1. So those are our 6 trigonometric functions of 45 degrees.